Here's the first page of the notes. And I'll put some perspective on this. In calculus, we're interested in, among other things, in optimization, finding what's the maximum of a function, what's the minimum of a function. You've been doing that since calculus 1. In calculus 3, we said this: suppose we have a surface z equals f of x, y, and we want to find local extrema, like a peak of a local mountain, but maybe it goes up higher over here, or the bottom of a local valley, but it goes down lower over here. We can do that with the second derivative test. We did that in 14.7. If we want the global extrema, if we have a function that looks like this, that's just over a closed region in the xy plane, a continuous function of two variables, then it's a surface and it has a maximum minimum. You can just find all the interior critical points, all the critical points along the boundary using calculus 1, plug them all in. The largest is the absolute maximum and the smallest is the absolute minimum. Those are the things we did in 14.7. Now what else can there be to do? Constrained optimization, that's today's topic. Here's the problem. Suppose we have the same thing as before, a surface z equals f of xy over the xy plane. And instead of saying what's the highest point in the mountain, what's the lowest point, we're going to say, subject to that I walk along this trail in the xy plane, this is my map in the xy plane, my trail map, I must be walking along this actual trail here on the mountain itself. Now what is the highest altitude I reach and what is the lowest altitude I descend to? That's the problem here. Subject to the constraint that we walk along this path in the xy plane, what's the highest z value we got? That's the constrained maximum. And what's the lowest z value we got? That's the constrained minimum. So that here is z1 and z0 on this particular example. Now to seek the constrained maximum, the good news in this section is that there's actually only one big theorem to do everything here. It's the Lagrange multiplier theorem. If f and g are differentiable functions, and f has a local maximum subject to the constraint curve, it doesn't have to. We're going to talk about that in this first example. At a point where the gradient of g isn't equal to 0, then the gradient of f is actually parallel to the gradient of g. That is, the gradient of f is a multiple, some number lambda, times the gradient of g. We call it a scalar in this context since the number multiplies a vector. So that's the big theorem. We won't go through the proof for this, but at the bitter end I will motivate it. I'll show you the outline of the proof and you can kind of see how it's done, which is actually the important part anyway. Here's the kind of problem you want to be able to do on the tests and on the homework. Maximize and or minimize f of xy equals some function, let's say 4x squared plus 9y squared, subject to a constraint, xy equals 4. One thing I don't think the book points out very well is it's actually really useful in a lot of cases to draw a sketch. If you do that, you can tell some of the things, like, does it actually have a maximum or a minimum? In this case, if you think about what z equals 4x squared plus 9y squared is, right? I can rewrite this as z equals x squared over a half squared plus y squared over a third squared, and recognize x squared over a squared plus y squared over b squared equals z. That's an elliptic paraboloid. So I know how to sketch that. I sketch that as elliptical cross-sections this way, parabolic cross-sections in the other two directions. And it goes up to infinity, of course. And now the problem is, subject to I walk along this trail, xy equals 4. Well, that's a parabola, right? Xy equals 4 is y equals 4 over x. You know how to draw that from algebra, right? It's got two branches, one here in the first quadrant and one here in the third quadrant of the xy plane. Subject to the constraint that you're along one of these branches, what's the lowest altitude and what's the highest altitude you reach? Here's the image up on the mountain, z equals 4x squared plus 9y squared. All the points that lie above here on this surface. And so you notice immediately that as you go out to infinity along this branch, the points go up and up. There can't be a maximum. So you can do that intuitively. That can certainly be made rigorous. But I think we'll put on our engineering cap for now and say it's obvious. Now, it does look like there's a minimum. In fact, you can make that rigorous too by saying this is actually a continuous curve, since it lies over a continuous curve on a continuous surface, and since it does this sort of thing, you expect it's going to have a minimum. In other words, you can put a greatest lower bound on it, and if it doesn't go below there, then you know somewhere along there, by theorem, the curve has to have some minimum if you have a continuous curve with a greatest lower bound. So we expect that, and actually if you think about it real carefully, here's another thing to tell from the sketch. This has symmetry, right? This has symmetry over the xy plane, and so does the hyperbola. These are going to go equally low, these two images over the hyperbola. We expect actually 2 points where there's going to be a minimum. So drawing a sketch gives you all those kind of things. And let's continue with that and just look for the minimum since there is no maximum. Now, here's the big theorem. It's only one theorem. You can do it. Write the Lagrange multiplier equation, like I called 1 on the last page. Gradient f equals lambda gradient g, where f is the function to maximize or minimize, and g is the constraint curve. G of xy equals 0 gives you the constraint. So first I write the constraint as g of xy equals 0. It was xy equals 4, so I say xy minus 4 equals 0. G of xy must be xy minus 4. Here's the function to maximize or minimize. So I take the gradient of f, partial with respect to x is 8x, partial with respect to 9y squared, y squared is 18y, and those are the components of the gradient of f. Partial of g with respect to x is y, partial of g with respect to y is x, gives you the components of the gradient with respect to y. Gradient of f equals some number lambda, the Lagrange multiplier, times the gradient of g. Now vectors are equal if and only if they have all their components equal. So that means 8x equals lambda y, right? 18y equals lambda x. Two equations. Unfortunately, this won't get our points that we need. Y, look, there's 3 variables, x, y, lambda, and only 2 equations. Typically, this doesn't reduce your solution possibilities enough that you can test them all. What we do is we also include this constraint. Here's the 2 equations from the Lagrange multiplier theorem. Together with the constraint, now we have 3 equations and 3 unknowns. Typically, you can reduce this to some finite set, at least in the problems you can, of points. And that you have to check to see which ones give you the minimum. You already know there's no maximum from the picture. So to solve star, the result of Lagrange multiplier theorem together with the constraint, you can do any way you want. It's generally 3 nonlinear equations and 3 unknowns, and there is no general way to do that. For linear equations, when you get those, there is a nice method that you learn in matrix algebra, linear algebra. You're welcome to apply that in special cases. Here, though, we have a nonlinear equation, xy equals 4. Linear equation means ax plus by equals c in 2 variables is a linear equation. So these 2 are linear, but this one's not. Anyway, the way you do these is up to you. You just have to be clever. And usually it amounts to substituting one equation into another to get rid of a variable. And so let's try that here. If I take in the first 2 equations and solve for lambda, lambda equals 8x over y from this one, lambda equals 18y over x from this one. Now I have lambda equals these 2 values, I can set them equal. Right? If I set them equal, I get 8x over y equals 18y over x, multiply through by xy and get this, and then divide by 2, and I've got 4x squared minus 9y squared equals 0, an equation in 2 variables. So by solving for lambda and each and setting these equal, I've reduced this to an equation in 2 variables, and now I've got here another equation in the same 2 variables, 2 equations and 2 unknowns, right? So now I can find the intersection of those. It's not too bad. I substitute from this one, y equals 4 over x, into this one, and now I'll get an equation in 1 unknown, right? So I've got, instead of 4x squared minus 9y squared equals 0. I got 4x squared minus 9, replace y with 4 over x squared equals 0. This equation, 1 unknown, rewrites like this. You divide it through by 4, multiply by x squared to get x squared, x to the 4th minus 36 equals 0. This is solvable, right? Factor it as x squared plus 6 times x squared minus 6 equals 0. This factor can't be 0. It's a non-negative number plus a positive number. By the zero product property, either this factor has to be 0 in order for the product to be 0, so it must be x squared minus 6 equals 0. Consequently, x is plus or minus square root 6 are the only possibilities for x. We only have 2 choices to look at by the Lagrange multiplier theorem, but we're not done, right? Put this into the 3rd equation because we also need y. The points we're going to check are not x, they're x, y pairs, right? So we'll put x equals plus or minus square root 6 into this equation, xy equals 4. and get square root of 6 times y equals 4, or minus square root of 6y equals 4. In which case, dividing by square root of 6, we get y equals plus or minus 4 over square root of 6, or plus or minus 2 square root of 6 over 3. That leaves exactly 2 points. When x equals plus minus square root of 6, you get this point. When x equals plus square root of 6, you get this point, and that's it. Lagrange multiplier theorem has reduced you to 2 possibilities for finding the minimum in this constrained optimization problem. So how do we define which one's the minimum? We already know from symmetry they're going to both be the minimum, it turns out. But let's plug them in and see. That's what you can do in general. When there's only 2 cases, you just plug them all in and see which one is the smallest, right? The Lagrange multiplier theorem guarantees that at one of these points it's going to have a minimum. So we plug it in and we get 48, and we get 48, sure enough, just as we expected. These both give a minimum. So the minimum value is the z value, 48, that occurs at these 2 points, plus or minus square root of 6, plus or minus 2 square root of 6 over 3. Here's the picture. We found this point here along the first hyperbola has height 48. We found this point here along the second branch of the hyperbola is also at height 48. Those are the 2 points at which you get minimum value on the elliptic paraboloid. Now a second example is worthwhile because some of the problems you have to realize that it's actually a Lagrange multiplier problem. Suppose I want to find the point on the line 6x plus 5y equals 12 that's closest to the origin. You'll find in lots of these problems where it's supposed to optimize something, you can rewrite it as a Lagrange multiplier theorem. This is kind of a classic one here. What's the point on the line that's closest to the origin, I wonder? Well, I'm trying to minimize something, the distance, which is, what's the distance from the origin to any point? This is just the distance from x, y to 0, 0, the distance formula, right? It's square root of x squared plus y squared. I'm minimize that, subject to the constraint that 6x plus 5y equals 12. So I have to, I've rewritten this as a Lagrange multiplier problem now, right? But this is not such an easy thing to work with as partial derivatives, square root of x squared plus y squared. So we realized cleverly that this will be minimized, the square root of x squared plus y squared, when x squared plus y squared itself is minimized. That's because square root is an increasing function. All right? So it'll be minimized when its argument is minimized. Here's the problem in Lagrange multiplier form: minimize f of x y equals x squared plus y squared, subject to 6x plus 5y minus 12 equals 0. So we'll call this g of xy, whatever is equal to 0 in the constraint curve, the object to minimize f, and we get, by the Lagrange multiplier theorem, gradient f equals lambda gradient g. 2xi plus 2yj is the gradient of x squared plus y squared. 6x plus 5y minus 12 equals 0 has gradient 6i plus 5j. That multiplies lambda. So this gives us 2 equations by setting their 2 components equals. 2x equals 6 lambda is the first, equates the first components. 2y equals 5 lambda equates the second components. And then the constraint curve, so we have 3 equations and 3 unknowns. 6x plus 5y equals 12. All right, now there's no standard procedure. These actually happen to be all linear equations. Some of the problems are like that. If you remember linear algebra, do them that way. You can add multiples of equations to another and eliminate variables that way. They call it elimination. There's a particular procedure called Gaussian elimination. Or we can do the same as our last example. We can solve for a variable one equation, substitute it in the other. It's a real common procedure. I think it works on all these problems. So from the first equation, suppose I solve for x in terms of lambda, right? X is 3 lambda. And if in the second equation I solve for y in terms of lambda, y is 5 halves lambda. And now I substitute those into the third. 6 times 3 lambda plus 5 times 5 halves lambda equals, the 12 is off the end there, equals 12. By substituting these into the third equation, we got rid of x and y. We have an equation just in lambda. So sometimes a little cleverness saves you some trouble here. Get rid of the fractions. Multiply that through by 2. Now, this says on the left, 61 lambda equals 24, or lambda must be 24/61 first, from which I can deduce by x equals 3 lambda up above, that x is 72 over 61, and by y is 5 halves lambda up here, that y is actually 60 over 61. Those are the only possible points where there could be, that is the only possible point where there could be a minimum distance. We know there's no maximum once again because on the line, here's a line sketch in the xy plane. It goes on forever. You can get infinitely far away from the origin, so there isn't going to be a maximum. But there has to be a minimum point, right? Euclidean geometry says you can drop a perpendicular, and there's a unique point at the end of the perpendicular that's the closest point of the line. So you do that, you say there's exactly one minimum. This is the only point that satisfies the Lagrange multiplier theorem, so that's the minimum right there. 72 over 61, 60 over 61. Plug those into F to actually find out what the minimum distance is. Okay, so now I also said that I would do the derivation, the outline of the derivation of the proof. That goes over on the following. I pulled this picture from your book rather than try to draw it myself. Why, you might ask, well, does this theorem work? Well, it works like this. If you think about z equals f of xy as that mountain, that surface, it has level curves, right? If you intersect it with planes and then project those intersection curves down in the xy plane, you get curves like this. This is like altitude 4 on the mountain. This is altitude 3 on the mountain. This is altitude 2 equals the mountain. Altitude 1 on the mountain, a topographical map showing the isoplex of the corresponding to the mountain z equals f of xy. Now, also your constraint curve, g of xy equals 0 is some curve in the xy plane, some differentiable function g of xy. And what the Lagrange multiplier theorem is saying is that the gradient of f is parallel to the gradient of g, meaning it points in the same or opposite direction, the two gradients do. Now you think about it, we have a theorem that says the gradient is perpendicular to the level curves of f, right? That was one of our theorems. And so we expect it to be perpendicular to the isoplex, for instance, at this point. And also, if you think about it, g of xy equals 0 is a level curve of z equals g of xy, right? This is the level curve for z equals 0. And so the gradient of g is also going to be perpendicular to this curve. Now, if you really think about it, where do you reach your highest altitude, assuming the mountain is sitting up, coming out of the page here, the z-coordinate coming out like this? Where do you reach the highest altitude? Well, if you're walking along this trail, you're at lower altitudes. Here you get to a particular altitude, here a little higher. The highest altitude is when you just come tangent to this isoplex of f, right? So it's when the g curve and the f curve are just tangent to each other that you get a maximum. You get isoplex corresponding to higher and higher altitudes until you just touch the level curve right here, and then you start going down to lower altitudes towards these isoplex with lower altitudes attached to them. Well, what that means is, if they're going to be tangent, that their normal vectors have to be in the same direction or opposite direction in order for them to have the same tangent line. But that means, since they're normal vectors of the gradient, that their gradients have to point in the same direction as shown here, or opposite direction. So gradient of f, remember, is perpendicular to the level curves of f pointing in the direction of steepest descent, so it goes this way since the isoplex are going up in this direction. Gradient g maybe points in this direction, maybe points in this direction, but those are the points at which you have a possibility of getting a constrained maximum or minimum, is when the curve g of xy equals 0 is just tangent to a level curve of f. Well, I hope that helps you do the homework. I'll send you some news shortly, and I hope you're having a great break. This is all section 14.8. Give it a try.